So let's start this chapter by laying out some definitions. So how do we define energy? Well, energy is anything that has the capacity to do work. And energy can happen in a lot of different ways, like a collision can be energy. It's just when energy can be transferred from one object to another object or from one system to another system. We're going to take a look at systems and what that means in a few more slides, but for now we can tend to think of energy as anything that has the capacity to do work. Now we've got a new word in here, which is work. What is work? Work is basically a force acting over a distance. So which is kind of a very broad definition. Basically, force is making something change. You could think of it that way. So that could be what you could think of as work, something that requires energy to create a change in something. It could be the force as a result of moving across a distance. Now heat. Heat is the flow of energy from one object to another, from one system to another. And we measure heat in terms of temperature. So these are all important concepts and language to get into place so that we're not kind of floundering as we move through this talk. So we could think of heat and work as two different ways that an object can exchange energy with other objects. All right. So what kinds of energy can we have? How can we categorize and quantify energy? Well, we can think of energy as energy of motion. So things can be already in motion, already doing stuff, and we would think of that as kinetic energy. So that's your typical 2-year-old with their eyes open and the world at their little grubby fingertips. A 2-year-old is in constant motion. They are kinetic energy. Another type of energy is thermal energy, and this is energy that is associated with temperature. We could think of it in terms of heat. So thermal typically means heat. You have your thermal underwear here in Maine. You need that because it helps you stay warm, so it's all about capturing that heat. So thermal is heat energy. You could also have something called potential energy. This is energy that is stored in an object or energy associated with composition and maybe even position of an object. So in the picture here, what we see is the woman or the man is holding a ball above a table, and that ball, by virtue of being above the table and on the planet Earth with gravitational pull, is potential energy. Because once that person lets that ball go, it'll no longer be stationary. It will no longer be in its potential state. It will now be in a state of movement, which will then move it into the category of kinetic energy. So this is one type of potential energy. If we reread our definition, it says energy associated with composition. Well, think about a stick of dynamite. Dynamite is not explosive until you light it, but its composition means that it has the potential to be very explosive. Why not reuse the word more than once? All right, so that's what we mean by composition. So this is energy that is stored as a result of composition or position of an object potential. Here's a little flow chart to help you think about what's happening. So we have energy, which is the capacity to do work. It's either energy that's already taking place or it's energy that could be taking place. So energy that's already in motion could also include thermal energy, which is that heat transfer, heat moving into an object, heat moving out of an object. So, but there's still that bit of motion as a result. So kinetic is kinetic energy has to do with motion. Potential energy is energy that is stored in a system. Things are not in motion yet, and potential energy could be due to position of an object, that is something that is high up that could fall, or is due to its chemical makeup. So chemical energy could, it says here also associated with positions of electrons and nuclei. Well, we've looked at a lot of that sort of stuff already. So anyway, flow chart, I like the colors. Some other forms of energy we have here listed are electrical energy. That's the flow of charge over like a wire or through water. Heat or thermal energy, we've already talked about that. It's a form of kinetic energy. Light or radiant heat, kinetic energy associated with energy transitions in an atom. Remember those electrons hopping from a low energy orbital to a high energy orbital and then relaxing back in? That is your light energy. So light energy gets released in the form of photons when those electrons relax back down into those lower energy state orbitals. That's how we get to see color, things like that. Nuclear energy, potential energy of the nucleus of an atom. So as long as the nucleus is intact, things are nice and calm. But boy, you try splitting those nuclei apart, and there's some exciting things that can happen. We discovered that sort of stuff back in the 40s. And then there's chemical reaction, which is the potential energy due to the structure of atoms and the attachment of atoms to other atoms. So that's kind of a recap of some forms of energy, and it even tells you kind of where they fall in the kinetic potential realms. And when we measure energy, of course, it's going to have a unit, and the unit is going to be the joule. The joule is a contrived unit. It comes as a result of kilograms per meter squared over milligrams times meter squared times over second squared. There, I'll get it out in just a second. So it is it has to do with mass and speed of something. So that is how we can measure joules. Now, it's just good to know how we get to the joule, and there might be a homework problem where we have to know that 1 joule is equal to 1 kilogram meters squared per second squared. I think there's one homework that asks you to make that calculation or use that as a conversion factor. But for the most part, in this unit, we're going to be focusing as the energy of the units of energy as just the joule. Now, there's another type of energy unit that's called the calorie. Now, a calorie is defined as the amount of energy needed to raise 1,000 grams of water 1 degree Celsius. That's how a calorie is defined. Now, when you look at the package of, I don't know, your ring dings or your Milky Way or whatever it is you're eating, and you flip it over and you see calories written there, what you see there is calorie with a big C. Big C has a different value. It is equivalent to 1,000 little c calories. So the big C calorie is like a kilocalorie. So that if you go to McDonald's and you eat the, I don't know, what is it, the Big Mac? It's 540 big C calories, and it's 540,000 little c calories. Yes. It is. So, yeah, if you're working a homework problem and you see the difference between little c and big C, it's different by a factor of 1,000, and that's because the big C is equal to 1,000 little c's. Okay. And your author is kind enough to give you a conversion chart between different types of units, so we can correlate a little c calorie to joules. We can do a kilocalorie to little c calorie, so big C calorie to little c calorie. And we can also do kilowatt to joules. So we can do some of these conversions. And I bet you have some homework problems that are going to make use of this chart. All right, so we're talking about thermodynamics at this point. And the word thermodynamics, what does that mean? Well, the word dynamic means that something is moving, and the IC ending means pertaining to. So this is pertaining to something that is moving, and in this case, we're talking about thermo, which means heat. So the study of thermodynamics is the study of energy and its interconversions. And it says, and we could think of it as the movement of heat in the universe. There is a law of thermodynamics, and it shouldn't come as a surprise that this law is the law of conservation of energy, which basically means that the total amount of energy in the universe is constant. We don't create energy, nor do we destroy it. When we're creating a chemical reaction, energy remains the same in a system. It says how you think about it is what makes the difference. How are you defining your system? So that if you define your system too narrowly, then it appears that things are escaping, and that perhaps you have created or destroyed something in the process. But if you think about energy in terms of thermal energy, and we're going to look at this again, so this won't be the first time you hear it, or the only time you hear it. It'll be the first time you've heard it, but not the only time you hear it. That if you look at a system that is creating heat, then you have to think of heat as part of the product of that system. Otherwise, without taking into consideration the value of the heat that gets created, it would appear that you had actually lost something in a chemical conversion. So we have to be mindful now and start thinking in terms of systems. So when we think of the universe as a whole, we don't create energy, nor do we destroy it. It just gets transferred from one object to another, or from one state to another. So you've heard me talk about systems. This is something that has not been talked about until we get into this chapter. And prior to this, we have looked at chemical reactions in terms of isolation and not really paid much attention to whether heat flows into a reaction or whether heat flows out of a reaction, or taken anything else into consideration. But now we need to, because we're dealing with heat, and heat does move in and out of reactions. So we have to come up with the definition of a system. Now, a system is defined as part of the universe that is being studied. So we can scale it down and look at kind of a closed system or an enclosed system, or we could look at the universe as a whole. For Chemistry 1, we're going to narrow up the spectrum and look at systems that are pretty small. That's a good thing. So one of the components of the system is going to be the surroundings. And the surroundings are going to be everything else in the universe with which the system can exchange energy. So think about if you were to take methane gas and oxygen and combust it, that is, set it on fire, you're going to create water and carbon dioxide. But then you're also going to create a great deal of heat. And where is that heat going to go? Well, a lot of that heat is going to move into the surroundings. So let's say that you were, barbecuing something, and you turned on your gas grill. It would be a gas grill. That would be a propane gas grill, and you light the propane, and here it is cranking out. It's burning up. It's making water. It's making carbon dioxide, and best of all, it's making heat. And that heat is going to transfer from that chemical reaction of those bonds being broken between carbon and oxygen and hydrogen. So that energy gets released, and then it's going to travel through the air until it reaches your hot dog or your burger or your chicken or whatever it is that's sitting on your grill. So that heat escapes into the surroundings, and then it will be absorbed by a different system, which in that case is your chicken or your burger or your hot dog. So thermodynamics, again, that study of energy exchange. If we have an energy exchange, then we have to be able to talk about it. And we are going to use the terms exothermic and endothermic. So if you have energy flowing from a system out into the surroundings, that is energy flowing away from a chemical reaction, that would be exothermic. So a combustion reaction where we're creating heat is an exothermic reaction. Now, energy can also flow into the system from the surroundings, and that does happen. And when that happens, we're drawing heat from the surroundings and putting it into our chemical reaction, into our system that we could be thinking of. And when that happens, we have an endothermic reaction. And yes, both of those happen. If we were in lab, I would give you examples of both of those. We'd actually do some stuff where you could feel the physical effects of heat being released from something reacting with water, and then feel the cooling effects of something reacting with water and drawing heat or thermal energy from the surroundings. So those two things do happen. So now that we know that energy is neither created nor destroyed as a result of a reaction, we need to think in terms of a system. And a system is going to be all of the potential energy of a system plus all the kinetic energy of the system. So that's how we would quantify the energy of a system. We look at everything that is about to happen, everything that might already be in motion, and then we take into consideration the transfer of energy from something that is potential energy into something that is kinetic energy. So that is what we're going to be looking at in the next few slides. So when we talk about energy flow, we're going to be talking about changes in energy. And the way we note changes in energy or changes in anything when we're writing it down is we use the symbol delta right here. That's a capital D written as the triangle. It's Greek, it's a Greek symbol, and it stands for change. So if we were to read this sentence, we would say that the change in the energy of the universe is basically equal to 0, which means that the change in the energy of the system plus the change in the energy of the surroundings is also going to always be equal to 0. So that your final amount of energy less your initial amount of energy should be equal to 0, or there is going to be some sort of transfer of energy. Now you may have some things. So we've talked a little bit about systems in this chapter already, and we have to be able to measure the energy change in a system, and it means we have to define the system, and we define the system or the energy of a system as the internal energy being the sum of the kinetic and the potential energies of all the components of that system. Now when you look at the sum of these energies, and you're measuring these energies, what you have to take into account is the initial conditions as well as the final conditions. And in some cases you'll make note of the process that gets you from the initial to the final. When you're doing what's known as a state function, this is a mathematical function where you're only looking at the values at the beginning of the condition and the value at the end of the condition, and you're not really concerned with the process that got you from the initial to the final. So why is this important? Well, let's go to the next slide. So here's an analogy of the difference between looking at initial values and final values in a system. So say that you were going to climb this mountain and you were going to go 10,000 feet. One path that you could take might look like this, where you start at the bottom and you go back and forth, taking this winding path all the way up. And this path will get you from 0 feet to 10,000 feet. And in order to do that, you'll go 12 miles to do that. The other path also starts at 0 feet, takes you to 10,000 feet, but it's on the side of the mountain, goes up a steep path, and you only go 5 miles. Regardless of which trail you take in a state function, you're only going from 0 feet to 10,000 feet, and it doesn't take into consideration how you got there, whether you took the yellow path of 12 miles or the red path of 5 miles. So that's a state function. Can you see kind of a flaw with the state function? Yeah, because there's a lot of energy that goes into taking a winding 12-mile path. There's also a fair amount of energy that goes into taking a very steep 5-mile path. So, but a state function doesn't consider the path. It just takes into consideration the beginning value and the ending value. So when you have a reaction, part of what happens is some sort of a heat exchange. You'll either gain heat as a result of the reaction or you'll lose heat as the result of a reaction. When you lose heat, that is when your reactants come together, create a product, and part of the product that gets created is heat. That's known as an exothermic reaction. So we say heat is released in the process of making the product. So you could almost think of heat as being part of the products in an exothermic reaction. So that's one way we can look at reactions, or that's one type of reaction that you can have, is the release of heat. You can draw an energy diagram that shows the exothermic process. So let's say that you had a diagram that showed increasing internal energy. When you're taking carbon and oxygen and you're putting them together to create carbon dioxide, You are starting off with high energy reactants, and as a result of that reaction, you're going to end up with a low energy product. And part of that reason why carbon dioxide is low is because you're releasing some of the heat, some of the thermal energy of the system into the surroundings. So that's one of the natures of nature of an exothermic reaction, is that your energy flow goes from the system into the surroundings. So you'll see a loss of the energy in the system, but you'll see a gain of energy in the surroundings. And we could think of it this way, that when you lose energy in a system, you're going to gain that energy somewhere, and it's got to be in the surroundings. So this is how an exothermic process works. Now, the opposite of an exothermic reaction is an endothermic reaction, and this is one where heat is input into the process in order to make it happen. So we've got our equation that we ran forward in the last couple of slides. Now we're running it basically in reverse. We're starting with carbon dioxide, and we're going to make carbon and oxygen. Now, in order to run this reaction, it's going to require the input of heat in order to get those high energy products of carbon and oxygen. So you have a low energy carbon dioxide, which is now our reactant, and we're going to put some energy into the system and create carbon and oxygen. So let's draw an energy diagram for this endothermic reaction. So in this scenario, we're starting off with low energy reactants, which in this case is carbon dioxide, and we're going to put some energy into the system. So our change in energy of our system is going to be in the positive, and we're going to create our high energy products as a result. So if the reactants, have higher internal energy than the products, then the change in energy will be negative. So in this case, we're going to be pulling energy from the surroundings and dumping it into the system, so that the energy of the system, the change in energy of the system, is going to be positive. And because the surroundings are experiencing a loss of energy, the change in energy of the surroundings will be a negative. So we can think of it this way, where we have the energy of the system gaining energy, and it's got to come from somewhere, and it's coming from the surroundings. So we can summarize what we just talked about on this slide, and it says that if the reactants have higher internal energy than the products, then the change in energy of the system is said to be negative, because energy will flow out of the system and into the surroundings. What are we talking about there? Well, we're talking about an exothermic reaction. If the reactants have a lower internal energy than the products, then the change in energy of the system is said to be positive, because energy flows into the system from the surroundings. That is an endothermic reaction. The internal energy of the system can be treated in a similar manner. The energy flow out of a system is written like a withdrawal and therefore carries a negative sign. And energy flowing into the system is much like a deposit and will carry a positive sign. So when you're working these equations, that positive and negative, and you'll want to include the positive and negative signs when you're talking about the changes in your energy, will tell you whether we have energy flowing into the system or energy flowing out of the system. When we look at energy exchange in a system, it's going to depend upon a couple of things. One of those things is going to be the thermal energy that gets moved around and the work energy that is part of that. Now, when we're talking about thermal energy or heat and work, we're talking about things that are not spoken about as a state function. In fact, their values are going to depend upon that process. So now we're talking about actually looking at the yellow path up the mountain or the red path up the mountain, and the heat and the work done in a system to give us an energy shift are ways that we can look at that process and move away from the simplistic nature of measurement under the state function concept. So because we have the two values of heat and work, that means inherently that the energy exchange between the system and the surroundings will either be through heat or through the work that's done. If we're talking about heat, which is the Q from the last couple of slides, then the heat is the exchange of that thermal energy between a system and its surroundings. The way we measure that is through something known as temperature. Temperature is the measurement of thermal energy in a sample of matter. And like many things, temperature will flow out of a system and into another system until an equilibrium is met. And when that happens, that's called a thermal equilibrium. Now, we've all had this experience. It shouldn't come as any sort of surprise. So you, I don't know, you can take an ice cube and drop it in a cup of warm water. Say like you made your coffee too hot, or you wanted your coffee to be at a different temperature than it was. You take a piece of ice and you drop it in there, and the ice is going to lose heat, and your cup of hot coffee will I should back that up. Your ice is going to gain heat, your coffee will lose heat until there is some sort of a balance that gets achieved between what was the ice, which eventually is going to turn to water, and the water that was the coffee. And it's not like the coffee is going to continue to get to a freezing point because it has ice in it, nor will your ice come to a boil because it is in boiling hot coffee. There's going to be that happy medium where the energy flows from one system into another system until there's just this balance that gets achieved, and they both end up being the same temperature. So heat capacity tells us about the ability of a substance, some form of matter, to absorb heat before it changes temperature. I guess that's the imperative thing there. So when a system absorbs heat, its temperature is going to increase. The increase in temperature is directly proportional to the amount of heat that is absorbed. And that's what is called the heat capacity. Now, not all substances have the same heat capacity. Some things can actually absorb a fair amount of heat before the substance itself undergoes a temperature increase. Some things have a very low heat capacity. In fact, it doesn't take much at all for their temperature to increase. So, for example, if you want to buy really good cookware, it's typically going to have copper involved in it, because copper has the ability to transfer heat very quickly, so that you're not wasting a lot of your energy from your stove heating up your pan in order to cook your food. So that heat gets conveyed very quickly, very evenly with copper, and that's why your higher grade cooking cookware will have a copper core in it, and it has to do with that ability of copper to absorb heat easily. Something that doesn't absorb heat easily is water. Water takes a long time to boil, and it takes a great deal of energy to get water to boil. That's why we say a watch pot never boils, because it seems to take forever. So heat capacity is a great thing to know, but there's a little bit more to it. For instance, how much matter you have matters. So the more matter you have to heat, the more heat it requires to heat that matter. So for example, 200 grams of water requires twice as much heat to raise its temperature by 1 degree Celsius as does 100 grams of water. So the same substance, if it has more mass, it's going to take more heat. So there's this ratio that goes into the mass and energy relationship. The heat capacity of the object also depends on the type of matter that you have. So for instance, 1,000 joules of heat will raise the temperature of 100 grams of sand to 12 degrees Celsius. But it will only raise the temperature of 100 grams of water by 2.4 degrees Celsius. So six times greater there for sand than it is for water. So water is one of those substances that has a very high heat capacity. It can take a lot of heat before it sees a temperature increase. So the way we quantify heat capacity is that we have to know the mass of the substance that we're dealing with, how much stuff we're dealing with. We need to know the specific heat of the material, that is the unique property of the material to absorb heat before it increases 1 degree Celsius. And then we also need to know the change in temperature. Now, I haven't said this yet, but I'm going to point this out so that nobody seems to be mystified by it. But this triangle right here, that is the Greek sign delta, and mathematics use delta to indicate a change in value. So when we see delta t, what that's implying is that we understand that it was an initial value and now there is a final value, and we're going to find the difference. And the way you find the delta t is you take your final value and you subtract your initial. I'm going to say it again because it's always a problem. You take your final value and subtract your initial. So that's how that is done, and then you're able to calculate Q. So, and oh yeah, by the way, where are you going to find the specific heat value? You're going to go to a chart and find it. There's a chart in the book that will list out several of these, like copper and aluminum and water and a few other things. So here is the table from the book that lists out some specific heat capacities of common substances. Now, the specific heat capacity in this chart is listed as joules per gram degrees Celsius. Now there's other values of a specific heat, but for this class and the problems that you're going to be working that I assign you, you'll be using these values with joule over gram degrees Celsius. So I think that seems like there is a problem where you have to change the units. I could be wrong. I'm not looking at the book, so I don't have that off the top of my head, but this is one of those things that you can have a different value depending upon what goes in to do the calculation. All right, so the measurement of a substance's intrinsic ability to absorb heat is known as specific heat. And each substance has a unique value, and it's kind of like a fingerprint for that substance. And it's based upon how the substance comes together via molecular forces, the size of the molecules, all that kind of stuff. And in each case, it ends up being very unique. So if we look here, we can see that, for example, where is copper? Copper comes in here as a pretty low heat capacity. And if we come down here to water, water is pretty much the highest heat capacity that we deal with in Chemistry 1 and Chemistry 2. It takes a lot more energy to get water to increase in temperature than it does copper. Copper just absorbs that heat and increases its temperature almost proportionally, and then off it goes. All right. So let's look at the example 9.2. It says that you found a penny minted before 1982, when pennies were still made purely of copper. Now pennies are not made of pure copper. They have a zinc core and a copper outer covering. So if you have a solid piece of copper, as you would with something minted before 1982, you could kind of figure out some information about it. So we're being asked how much heat is absorbed by the penny as it warms from the temperature of the snow, which is a -8 degrees Celsius, to the temperature of your body, which is 37 degrees Celsius, and assume that the penny is pure copper and has a mass of 3.10 grams. So can we solve this problem? Why, yes, we can. So we're given the mass, which is something that we're going to need, and we have its initial and final temperature, and you can go to a chart to find its specific heat capacity. So you can find the heat absorbed with all of this information. So here's our given values. We have our mass of our penny at 3.10 grams. We have our initial and our final temperature. And we are going to find Q, and our equation is right here. Q equals M, as in mass, and the specific heat of copper and the change in the temperature. So this is going to be our conceptual plan. So we have these values right here, or we can get them, and we need to solve for this one. And the relationship that we're going to use to do this is the equation Q equals M times specific heat times delta T. All right, so at this point, we need to do a little bit of math, and we want to calculate the change in our temperature. And you'll see here the change in our temperature is the final temperature reading minus the initial temperature reading. And that is 37 degrees minus a -8, and it's a 45-degree temperature change. So now we can plug in all of our values. So we have our mass, we have our specific heat of copper, we have our temperature change, and you can see all the repeating values cancel out, and the amount of heat that was absorbed by the penny from the moment we picked it up off the snow was 53.7 joules. And that's how you work those problems. Now, in that equation, that example that we just looked at heat flowing into one system. But if we're holding a penny in our hand and it's absorbing a certain amount of heat, where's that heat coming from? Well, the heat is coming from us. So there's two systems being affected in that example. We have the system that is the penny, it's undergoing a heat gain, and our hand, which is another system, undergoing a heat loss. So that's what we're going to get into in these next few slides, is looking at the heat transfer and final temperature and see if we can correlate this to two systems, the two systems that are being affected. So when two objects at different temperatures are placed in contact, such as your hand and a penny picked up from the snow, heat will flow from the material at the higher temperature to the material at the lower temperature. So from your hand to the penny. Heat flows until both materials reach the same temperature. The amount of heat energy lost by the hot material will equal the amount of heat gained by the cold material. Hopefully that makes intuitive sense. Let's hope. So let's say we have a beaker of water at room temperature, and we drop into it a piece of metal that we have heated up to 70 degrees Celsius. So our metal is at 70 degrees Celsius and our water's at, let's say 19 degrees Celsius, which is roughly room temperature. What's going to happen? What's going to happen? Well, our metal is going to put off heat until it reaches, I don't know, something like maybe 25 degrees Celsius. And where's that heat going to go? It's going to go into the water, and it'll heat up the water until the water reaches 25 degrees Celsius too. So when both of these objects, that is the water and the metal, have reached the same temperature, we've had that thermal equilibrium get established. And it's at these initial and final values that we can figure out how much energy was transferred between them. So let's take a look at that. So we had a lot of energy in the metal, not so much energy in the water. And as the metal lost energy, the water gained it until an equilibrium was established. This is the concept that we're dealing with. And Q is our measurement of the thermal energy that was transferred between the two. So we can use this equation right here to figure out some stuff between the two systems. Here we go. I'll get it out. So let's say that we had the Q for the metal, the heat for the metal, and let's just say that our metal was 13 grams and it was copper, so it has a specific heat of 0.385, and our temperature final was 25, and initially it was 70. So we're going to subtract 70 from 25. And once we do that math, we end up with a negative 225.25 joules. Now, does this make sense? Well, we went from high energy to low energy, and in order to do that, we had to cast off heat. And in order to express that we cast off heat, our energy needs to have a negative value. So yeah, this makes sense. So if our energy of our metal has a negative value, then the energy of our water must be the opposite of that. So we could take the opposite of Q of our metal, which would be the opposite or the negative of negative 225.25 joules, and we could find out that the energy that the water absorbed was 225.25 joules. So that's how that works. So somebody's losing it and somebody's finding it. And This is one of the reasons why knowing positive and negative and what that means is important to you. So now let's say that we had a piece of metal that was in the freezer, and it comes in at 0 degrees Celsius, and we drop it into our beaker of water, which is room temperature. What's going to happen now? Well, now our metal is going to absorb heat from the water until, let's say, it reaches 15 degrees. Now our water, on the other hand, is going to experience a downturn, and it's going to chill a little bit and go down to 15 degrees Celsius. So what is happening? Well, now we have the energy of our metal not being so robust, and relative to our water, our water is pretty substantial as far as heat energy. So what ends up happening is our metal is going to absorb water heat, and the water is going to be the one that gives it to it until we end up establishing a thermal equilibrium. Taking a look at our equation again and using the same numbers as before, except with the changes in our temperature, we started out at 15 degrees Celsius and we ended at 0 degrees, we started at 0 degrees Celsius and we ended with 15 degrees. There we go. See, I made the mistake too. And do the math. And now we end up with a positive 75.08 joules for our metal. So what does that positive mean? That positive means that we have taken in energy into the system, which in this case is our little nugget of copper, and we've taken it in from the surroundings, which is in this case the water. So we can take the heat of water and know that it's going to be the opposite of whatever the heat of our metal was, and in this case it's going to be the opposite of 75.08 joules, which means that water lost 75.08 joules of heat. So this is how these equations are worked when you're asked to compare two systems and what's happening. Now, what would happen if you were given this value? And let's say that you were given the change of temperature, and maybe you were given the mass. Would you be able to calculate the specific heat of an unknown substance? Yeah, you could. At that point, it becomes an algebraic problem. So as long as you're given either Q or G, and either one of these values, you can do a calculation and figure out everything else. So let's say that you knew the heat that was evolved, and you knew the mass of your substance, and you knew the specific heat, and I gave you an initial temperature. Could you figure out what the final temperature was? Yeah, you could. You would basically be doing algebra at that point. So I believe that's what a lot of the homework problems as well as the exam problems are, is seeing how well you understand this equation to set it up and then solve for it. So thermal energy is going to transfer heat from metal to water or water to metal depending upon the temperatures. And the exact temperature change is going to depend upon the mass of the metal and the mass of the water and the specific heats of the metal and the water. And with all of that put into an equation, you can summarize it by what we see here in the bottom, that whatever the metal, the heat evolved for the metal, it will be the opposite for the water. Don't be fooled by this negative sign. It doesn't mean negative. It means the opposite. The opposite. So if your Q of metal is 10, then that means that the Q of water will be negative 10. If your Q of metal is negative 15, then your Q of water will be 15. That negative means the opposite, because remember, it's coming from some place and going to another place. For someone, it will be a gain. For someone, it will be a loss. Another way that we can quantify work is by looking at the changes of pressure and the changes of volume in a system. Now, this may seem kind of like something random to study, but the reality is that we all drive cars, and cars operate with pistons. And pistons are basically creating work by altering volume and pressure inside of a cylinder. So let's see if we can understand what's happening here. So PV work, pressure volume work, is work caused by a volume change against an external pressure. In this case, we have a plunger in our cylinder that is pushing down and decreasing the volume and thereby increasing the pressure in that system. So when gases expand, the change in the volume will be positive. That is, the volume will gain. But when a system is doing work on the surroundings, but the system is doing work on the surroundings, so the work of the gas will be negative. Now, as long as the external pressure is kept constant, then the work is equal to the opposite of the pressure times the change in volume, as long as the pressure is kept constant. So we could say that the work of the gas is equal to the external pressure from our plunger times the change in the volume where the gas lives. So to convert the units to joules, we're going to use 101.3 joules being equal to 1 atmosphere liter. Atmosphere liter being a contrived units, but by the way, so are joules. So let's take a look at what we're talking about. So let's see, we're going to inflate a balloon, and in order to do that, you have to push the sides of the balloon against the air in the atmosphere. So if you inflate a balloon from a volume of 0.1 liters to 1.85 liters against an external pressure of 1 atmosphere, how much work have you done? Well, there's always some work to be done blowing up balloons. That's why I don't like doing it. It takes a lot of effort to do that. And it's because we are, we're working against actually more than the atmosphere. You're also working against the resistance of the rubber of the balloon. But hey, we're not going to talk about that. We're just going to leave that out of our system. Be glad for it. All right. So let's just talk about the pressure of the gases, internal and external gases. So let's see, what are we given? Well, we're given the initial volume of the balloon, and we're given the final volume of the balloon. So we're going to be able to find the delta V, which is the change in volume. And we're given that pressure, and we're assuming that the pressure that is working on the system, that is the balloon being blown up, will remain the same. So being able to find the work being done in this effort is not going to be that difficult. So we want to find the W. So the equation that we're going to use is W is equal to the opposite of the pressure times the change in volume. And there is our conceptual plan. And if we set this up in an equation, it'll look like this. We have, we're going to figure out the change in our volume first. So we take that final volume and subtract the initial volume, because that will give us the change in volume. Remember, we subtract the initial from the final. And so we're going to take 1.85 liters and subtract 0.1 liters, and we're going to have a change in volume of 1.75 liters. So now we can drop that into the equation, and the work that was done was a negative 1.75 liter atmospheres. Now, if we want to convert that into joules, we're going to use that conversion factor that we were given earlier on an earlier slide, this right here. And the units that you see go on top, so we're going to put joules on top and its equivalents in liter atmosphere on the bottom. And so we ended up doing negative 177 joules of work on that balloon to blow it up. So that's what happened. We did some work. Yes, we did. So now we have a new value to put into the equation as far as looking at the energy exchange between our system and the surroundings, and that is the exchange of work. This that we just worked with right here, involving pressure and the change in volume. So again, when we're looking at Q, we're looking at the exchange of heat energy. When we're looking at W, we're looking at the exchange of work. So you'll see there's no heat necessarily that's been exchanged when we blew up the balloon. But there was work that was done, and it's measured in joules as well.